Welcome to the Explainer. Today, we are going to build a roadmap, a really clear guide through the world of econometrics. Now, if you are preparing for the Indian Statistical Service exam, you know this is a huge part of your syllabus. Our goal here is to give you a clear, logical way to think about and master all the key concepts.
So, let's start with the big picture. You've got all these really elegant, powerful economic theories about how the world is supposed to work. But we all know the real world, it's messy, it's complex, it's just full of noise. So the fundamental question for any statistician or economist is, how do we bridge that gap? How do we test if our neat theories actually hold up in the face of messy reality?
And this slide shows you that problem perfectly. On the one hand, you have your theory, a nice, clean, straight line. You know, as income goes up, consumption goes up in a really predictable way. But then, you look at reality. You plot the actual income and consumption for thousands of real households, and you don't get a perfect line. You get a scattered cloud of dots. The magic tool that lets us find the true signal inside all that noise, that's econometrics. To put it really simply, econometrics is the toolkit we use to find credible, data-driven answers to economic questions. It's what lets us move from just an idea to actual, concrete evidence. So come on, let's open up that toolkit and start with the most basic tool inside. Okay, our journey starts with the most fundamental tool in the entire kit, the simple linear regression model. We usually estimate it using a method called ordinary least squares, or OLS. Just think of this as our starting point, our perfect, idealized laboratory setting. So this equation, this is our attempt to draw the best possible straight line right through that cloud of data we just saw. Y is the thing we're trying to explain, maybe consumption. X is what we think explains it, like income. And then there's epsilon. This little guy is so important. It's the error term, and it basically captures, well, everything else. All that real-world messiness that affects consumption besides just income. Now, for OLS to give us what we call the best linear unbiased estimator, you'll see that as blue all the time, our perfect little lab has to follow some very strict rules. These are the classical assumptions. We're assuming the relationship is a straight line, that those errors are pretty much random and they cancel each other out on average, and that the errors have a constant variance. But what happens when we leave the lab and step into the real world?
Yeah, as you probably guessed, the real world is almost never perfect. Our data is often, let's say, contaminated with problems that break those classical assumptions. And when that happens, the reliability of our results, well, it's suddenly under threat.
And here are the usual suspects. While there are a bunch of potential problems that can pop up, for your ISS syllabus and for our roadmap today, we're going to focus on three of the biggest contaminants you'll run into: multicollinearity, heteroscedasticity, and autocorrelation.
First up, multicollinearity. This is what happens when your explanatory variables are just too closely related to each other. I mean, think about it. Imagine trying to figure out the separate effects of a person's age and their years of work experience on their salary. Those two things tend to move together, right? So it becomes almost impossible for the model to untangle their individual impacts. It's like trying to give credit to just one of two synchronized swimmers for a move they both did at the exact same time.
Next up, we've got heteroscedasticity. And I know, it's a mouthful, but it's a pretty simple idea. It just means the spread, or the variance, of our errors isn't constant. The classic example is income and savings. Think about it. Low-income families don't have a lot of extra cash, so their savings amounts are all going to be clustered pretty close together. But high-income families, they have a ton of choice. Some save a lot, some spend a lot. The spread, or the variance of their savings, is way wider. That changing spread, that's heteroscedasticity.
And our third big contaminant is autocorrelation. This one is a really common problem when you're working with data over time, or time series data. It's when the error from one time period, say this quarter's sales numbers, sort of spills over and influences the error in the next quarter. A sudden shock or an unexpected event doesn't just vanish. Its effects can linger, creating a pattern in the errors that stretches over time.
Okay, so our model might be contaminated. Now what? Do we just throw our hands up and give up? No way. Econometrics gives us a whole diagnostic toolkit. We can first detect these problems, and then we can correct for them. Let's see how that process actually works. This table really lays it all out. There's a systematic process here. For each problem, you follow a three-step path.
You figure out the consequence, you use a specific test to detect it, and then you apply a known method to fix it. So for multicollinearity, the consequence is that our estimates get really unreliable. We spot it by looking for weird signs, like a high R-squared but low t-stats. The fix? Maybe drop a variable. Now look at the other two, heteroscedasticity and autocorrelation. Notice the consequence is the same for both. Our T and F tests become invalid. This is huge. It means we can't trust our own conclusions about whether a variable matters or not. We use different tests to find them, like the White's test or the Durbin-Watson test, and different solutions to fix them. But it's this structured approach that's so important.
But of course, the real world is even more complex than that, right? So our toolkit has to be even richer. The standard regression model is really just the beginning. Econometrics gives us these incredibly powerful tools to handle situations that go way beyond a simple one-way relationship.
For instance, we often have to deal with what we call feedback loops, or two-way causality. Just think about basic supply and demand. The price of an iPhone affects how many people want to buy one, right? But the number of iPhones available for sale also affects the market price. It's a two-way street. To model that, we can't use just one equation. We need what are called simultaneous equation models to capture that interconnected dance. And this brings up another super common challenge. A lot of economic decisions aren't numbers on a scale, they're simple yes or no choices. Are you going to buy a new car this year? Yes or no. Is a company going to expand into a new market? Yes or no. Our standard linear regression model just isn't built to handle that kind of binary yes-no outcome.
So for these more complex situations, we get to expand our toolkit. To analyze those yes-no decisions, we turn to things called discrete choice models, like Logit and Probit. When the effect of something, like a big advertising campaign, is spread out over several months, we use distributed lag models. And for data that evolves over long periods of time, there's a whole specialized field of time series analysis. These are definitely more advanced tools for further down your econometric road, but they are crucial for tackling real-world questions.
So here's the crucial point I want you to take away. This whole roadmap, it's not just a random list of topics to memorize. It's a logical progression. You start with the perfect, ideal case. Then you learn how to diagnose and fix the problems when reality gets messy. And finally, you expand your toolkit to handle even more complex economic behaviors.
And for all of you focused on the SIS exam, it's really important to see where this all fits. The number 7 you see here? That represents the number of sections in your statistics paper 4. Economics is just one of those sections. It's a vital piece of the puzzle, for sure. But it's part of a bigger arsenal designed to give you the practical, analytical skills you're going to need to be a really effective statistical officer.
Ultimately, the real goal here isn't just about memorizing formulas to pass an exam. It's about gaining the power to look at a messy cloud of data, to test an important idea, and to uncover the evidence-based truth that's hiding inside. It's about being able to bring real clarity to incredibly complex economic questions. Good luck with your preparation.